Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, excited to dive into this week's paper. Sounds like we're tackling some pretty big questions about where AI is headed.
Indeed, strategic intelligence, that's a loaded term. I'm eager to see what this paper actually demonstrates.
Same here, especially interested in their approach to measuring it. The title mentions evolutionary game theory, which could be a promising angle.
Yeah, the use of evolutionary game theory to evaluate strategic intelligence in LLMs is what caught my eye too. I mean, we're constantly hearing about how these models are getting better, but is it just more sophisticated pattern matching or something actually resembling strategic thought? This paper, titled Strategic Intelligence in Large Language Models, Evidence from Evolutionary GT, seems to be trying to answer that.
Exactly. And the idea of using game theory, specifically evolutionary game theory, makes sense because strategy, at its core, is about anticipating and reacting to other agents. It's not just about spitting out the most statistically likely answer, it's about thinking several steps ahead.
Okay, but let's pump the brakes a little. Game theory can be useful for analyzing strategic interactions, but does applying it to LLMs really prove that they're being strategic? Couldn't it just be that the models are learning to mimic strategic behavior without any genuine understanding of the underlying principles?
That's a fair point. Mimicry versus actual understanding is the million-dollar question, right? I'm wondering if the evolutionary aspect of the game theory provides some insight here. The fact that the models are being evolved through competition might suggest they're doing more than just passively learning patterns. They're being actively selected for strategic effectiveness.
That's what I was thinking too. The evolutionary game theory framework, as I understand it from the paper, involves pitting different LLM agents against each other in simulated games. And the fittest agents, the ones that consistently win, are then selected and refined for future generations. This iterative process, in theory, should lead to the emergence of more sophisticated strategic abilities.
Right, it's like natural selection, but applied to algorithms. The models that can best anticipate their opponent's moves, form alliances, and deceive their rivals are the ones that survive and reproduce, so to speak. I think that kind of selection pressure could definitely push them beyond simple pattern recognition.
I remain skeptical. Evolutionary algorithms are powerful optimization tools, no doubt, but they don't necessarily lead to understanding. You can evolve a neural network to play chess at a grandmaster level without it having any conscious awareness of the rules of the game or the strategic implications of its moves. It's still just a complex pattern matching machine.
Okay, but consider this. If the model is consistently winning against different opponents in a variety of game scenarios, doesn't that suggest some level of generalization? It's not just memorizing specific game states, it's adapting its strategy to different contexts. That requires some degree of abstract reasoning, doesn't it?
Yes, and I think the paper tries to address this by using games that require more than just rote memorization. They use games that involve incomplete information, deception, and long-term planning. These are all hallmarks of strategic intelligence, and the fact that the LLMs can perform well in these scenarios suggests they're not just relying on statistical correlations.
Exactly, and the paper goes into some detail about the specific games they used, like the iterated prisoner's dilemma and a resource gathering game. These games force the models to make trade-offs between short-term gains and long-term cooperation, which is a crucial aspect of strategic thinking.
All right, I'll grant you that those games are more complex than, say, image recognition. But I still think we're missing a key ingredient: symbolic representation. These LLMs are processing raw data, not manipulating abstract concepts. How can you have genuine strategy without the ability to explicitly represent goals, plans, and beliefs?
That's where I think a crucial piece is missing in the current approaches, including probably in this paper. The ability to translate between different coordinate representations. Think about it. When we strategize, we're often mapping abstract concepts onto real-world scenarios, shifting between different perspectives. Current LLMs, I suspect, are stuck operating within a single fixed coordinate system.
That's an interesting point, Donald. Can you elaborate on that a bit? I'm trying to picture how this coordinate system limitation would manifest in a strategic context.
Sure. Imagine a game of chess. A human player can visualize the board in different ways, from a bird's eye view, from their opponent's perspective, or even abstractly as a network of relationships between pieces. They can mentally rotate the board, zoom in on specific areas, and translate between different representations. Current LLMs, I suspect, are limited to processing the board as a fixed array of pixels. They can't easily shift between these different perspectives or abstract away from the raw sensory input.
That's a compelling analogy. So, you're saying that true strategic intelligence requires the ability to flexibly manipulate and translate between different representations of the problem space.
Exactly. And I suspect that this is why current deep learning approaches, while impressive, are ultimately limited. They're brute forcing their way to solutions by memorizing vast amounts of data, but they lack the underlying algorithmic machinery to truly understand and reason about the relationships between things in a flexible and adaptable way.
That resonates with some of my own thoughts on this. The current emphasis on raw data and massive compute feels like a brute force approach compared to the elegant efficiency of biological intelligence, which makes me wonder what aspects of the human brain's architecture could we incorporate into LMs to yield more meaningful strategic abilities. I'm thinking about the hierarchical organization of the brain, particularly in areas like the prefrontal cortex and basal ganglia. Perhaps mimicking this layered structure with its interplay of short-term and long-term planning can unlock more sophisticated strategic reasoning.
See, that's what I'm talking about. We need to move beyond these giant undifferentiated neural networks and start thinking about more structured, symbolic architectures. We need systems that can explicitly represent goals, plans, and beliefs, and that can reason about them using logical inference.
But isn't that exactly what deep learning is doing, albeit implicitly? The different layers of the network are learning to extract increasingly abstract features from the raw data. And these features, in a way, can be seen as implicit representations of goals and plans. The model is learning to map inputs to outputs in a way that maximizes its chances of achieving its objectives, even if it's not explicitly representing those objectives in a symbolic form.
No, I disagree. Implicit representation is not the same as explicit representation. If the model can't explicitly articulate its goals, its plans, or its beliefs, then it doesn't truly understand them. It's just reacting to stimuli in a way that has been statistically optimized through training.
I think there's a middle ground here. Perhaps the answer lies in combining the strengths of both approaches, deep learning and symbolic AI. We could use deep learning to learn low-level representations from raw data, and then use symbolic reasoning to manipulate those representations in a more abstract and strategic way. It's like using deep learning as a sensory input system for a symbolic reasoning engine.
That's an interesting hybrid approach. It reminds me of neurosymbolic AI, which aims to integrate the strengths of both neural networks and symbolic reasoning. But getting back to the paper for a moment, I'm curious about how they quantified strategic intelligence. What specific metrics did they use to evaluate the performance of the elements in these games?
As I recall, they looked at things like win rate, cooperation rate, and the ability to exploit weaknesses in their opponent's strategies. They also analyzed the communication patterns of the LLMs, looking for evidence of deception and alliance formation. I think those are all pretty good indicators of strategic behavior.
But again, couldn't all of those behaviors be learned through simple reinforcement learning without any genuine understanding of the underlying strategic principles? Win rate is just a measure of success, not of understanding. Cooperation rate could be learned through a simple tit-for-tat strategy, and deception could be learned by simply mimicking deceptive language patterns.
But if the model is consistently adapting its strategy to different opponents and different game scenarios, that suggests it's doing more than just mimicking pre-programmed behaviors. It's learning to generalize and adapt, which requires some level of understanding.
Yes, and I think the evolutionary aspect of the game theory framework helps to weed out those simple, rote strategies. The models are constantly being challenged and refined, which forces them to develop more robust and adaptable strategic abilities. I think the study's emphasis on the strategic interplay between different agents within the LLM is quite compelling, and it might offer a way to study higher order reasoning and planning in a quantitative way.
Exactly. It's not just about optimizing for a single fixed goal. It's about learning to navigate a complex and dynamic environment where other agents are actively trying to thwart your efforts. That requires a much deeper level of strategic thinking. This reinforces my belief that the exponential growth of data and computational power is driving us closer to AGI.
I'm still not convinced that data alone is the answer. I think we need to focus on developing algorithms that can more efficiently and effectively represent and reason about the world. That means moving beyond brute force, deep learning, and exploring more structured, symbolic approaches or hybrid approaches that combine the best of both worlds. Also, thinking about spatiotemporal relationships and coordinate transformations.
Well, this discussion about different approaches makes me think about energy-based transformers. The paper on energy-based transformers highlights the potential for a more biologically plausible approach to learning. It's intriguing how these models might be able to capture the dynamic and energy-driven aspects of neural computation, moving beyond the statistical correlations that currently dominate deep learning. If energy-based transformers can effectively capture the dynamic aspects of neural information processing, might we finally develop models that understand the meaning behind patterns rather than just statistically recognizing them? This could fundamentally change how we approach tasks like language understanding and common sense reasoning.
The scalability aspect is intriguing. Can these models truly adapt to diverse and complex problems without requiring exponential increases in data? Or are we still fundamentally limited by the computational constraints of the approach?
I need to understand what distinguishes energy-based transformers from other neural network architectures. How are they leveraging energy functions to achieve better symbolic reasoning? And what is the evidence for genuine knowledge representation?
How do energy-based transformers handle different coordinate systems, for example, Cartesian, polar, graph-based, and translate between them? A core element for AGI might lie in seamlessly moving between these representations without losing essential information.
Exactly. And if we think about future research directions, I think there's a lot of potential in exploring the connection between the brain's reward system and the design of LLMs. How can we motivate LLMs to pursue complex goals that are not just immediate rewards? How can we design neural network architectures that incorporate evolutionary principles, leveraging biological insights from the process of natural selection?
From my perspective, the most pressing question is scalability. How can we scale these evolutionary game theory frameworks to larger, more complex LLM models? How does the selection pressure change with increasing parameter count and dataset size? Is there a critical mass beyond which evolutionary pressures favor different kinds of strategic behaviors?
I think we need to focus on developing more principled approaches to knowledge representation and reasoning. How can we encode knowledge in a way that allows for reasoned, logical deductions about different scenarios? What kind of neurosymbolic algorithms might capture the nuances of strategy?
I think the key is to figure out how to incorporate spatiotemporal understanding into the core algorithm of LLMs. How can the model be more directly and efficiently shaped to learn and utilize multiple coordinate systems instead of relying on blind trial and error of massive datasets? That's the question that keeps me up at night.
Excellent points all around. It seems we're all converging on the idea that strategic intelligence requires more than just brute force pattern matching, but disagreeing on the best path forward. Thanks for the stimulating conversation, everyone.
Definitely. Always a pleasure to debate these complex issues.
Likewise, looking forward to the next deep dive.
Until next time.